Good morning, students. Today we will discuss some module of a module over a ring. So, definition is, let us take a module M over a ring R and a known empty subset N of M. Then we say that this N is some module of M over the ring R if two conditions are satisfied. First condition, this N is subgroup of M under addition. It means if we take two elements A and B from N, then A minus B belongs to N. And in the second condition, N should be closed under scalar multiplication. It means for every A belonging to N and R belonging to ring R, RA that belongs to N. So if these two conditions are satisfied, we say that N is some module of M over the ring R. Every module has two submodules which are called trivial submodules. The first one is identity and second is M. These two modules are submodules of M over the ring R. These are known as trivial submodules. In this definition, if the ring R, that is a field, in that case, this submodule becomes subspace of M. Now let us see an example of a submodule. In the first example, we will show that if we have a ring R and we take a left ideal of this ring, then this left ideal is R submodule of the left R module R. To prove this, let us take IV left ideal of the ring R. Now let us apply the definition of left ideal. By definition of left ideal, first condition, if we take two elements A and B from I, then A minus B belongs to I. And by second condition of ideal, for R belonging to the ring R and A belonging to the ideal R into A that belongs to I. So both conditions for being a submodule are satisfied by I. So we can say that I is submodule of R. Here in the whole section, if it is not mentioned, we are considering submodule as the left R submodule. Okay. Now our next example is, let M be an R module and X be an element of M. Then we are to prove that the set Rx, which is the collection of the elements of the form Rx, where this R belongs to the ring R. We are to prove that this set is submodule of M over the ring R. Now to prove this submodule, first of all, we show that this is non-empty. Now because R is a ring and every ring has additive identity, that identity element we have shown by 0. So identity into X, that belongs to Rx, and therefore we can see that Rx is non-empty set. Now the remaining conditions for being a submodule. So let us take two elements R1x and R2x belonging to the set Rx. Here R1 and R2, they belongs to the ring R. Now we have to prove that their difference belongs to the set Rx. So let us find their difference. Now this can be written as R1 minus R2 into X. Now because R1 and R2, these are the elements of ring R, and therefore R1 minus R2, that is also an element of ring R by definition of ring, and this is an element of R. So by definition of set Rx, this element will belong to the set Rx. So we can say that the set Rx, that is a subgroup of M under addition. Now in the next condition, let us take one element R1 from the ring R and an element R2x belonging to the set Rx. We are to prove that R1 into R2x belongs to the set Rx. Now by properties of module, because M is a module, so R1 into R2x, that can be written as R1 R2 into x. Now R1 and R2 are the elements of ring R. So by closure property, R1 into R2, that will again belong to the ring R. And therefore this element belongs to the set Rx. So we can say that Rx is closed under scalar multiplication also. So this proves that the set Rx is submodule of M over the ring R. Now, next our theorem is to prove that intersection of arbitrary family of submodules is a submodule. It means if we take a collection of R submodules of an R module M, that collection we have denoted here by the collection Ni. Here I belongs to the index set. We will prove that intersection of members of this family, that is also forming a submodule over the ring R. Now let us denote this intersection by the set N. N is the intersection of all the members of the family. Here I belongs to the index set. We are to prove that this N is submodule over the ring R. Now this is module over the ring R. Now to prove this, first of all we will have to show that this N is non-empty. To show that this is non-empty, because each Ni, that is a submodule of M, and therefore identity element belongs to each Ni because Ni is subgroup of M under addition. So this identity element, additive identity, that belongs to the intersection of all these Ni's, and this is N. So we can say that additive identity belongs to N. So N is non-empty subset of M. Now next we have to show that N is subgroup of M under addition. So let us take two elements x and y belonging to N. N is the intersection of all the Ni's. So if x and y belongs to N, it means x and y belongs to each Ni, and each Ni is a submodule of M. So x minus y belongs to Ni, and this is true for every I belonging to the index set. So we can say that x minus y belongs to the intersection of Ni's. So we can say that x minus y belongs to N. So we can say N is a subgroup of M under addition. Now our next condition is, in the next condition, let us take one element from the ring R, we have taken as A, and x from N. Again x belongs to N, it means x belongs to intersection of Ni's. So x belongs to each Ni, and because each Ni is a submodule of M over the ring R, so for A belonging to R, x belonging to Ni, A into x belongs to Ni, and this is true for every I. So we can say that Ax will belong to the intersection of these Ni's. We have proved Ax belongs to N. It means N is closed under scalar multiplication. So both conditions for being a submodule are satisfied. So we have proved that intersection of arbitrary family of submodules of a module is again a submodule. Now Next we define quotient module, or we can say factor module. So let us take M is left R module and N is submodule of M. We will define the factor module. To define factor module, we need a normal subgroup of M. Now because M is a module, so it is abelian group under addition, and N is submodule of M. Subgroups of abelian group are normal. N is submodule of M, so N is subgroup of M under addition, and therefore N will be normal subgroup of M. So we can say that the factor group M by N is defined, and that will also be abelian group under addition. And M by N is the set consisting of elements of the form of cossets formed by the elements of M. So if we take X belonging to M, then the cossets X plus N, such type of elements form the quotient module. Now, to prove that this defines a quotient module, we will have to define vector addition and scalar multiplication. So let us take two elements from M by N. First element we have taken X plus N, and second Y plus N. These are cosset type elements. Here X and Y belongs to M, and we define the vector addition in M by N by X plus N plus Y plus N is equal to X plus Y plus N. So in this way we have defined vector addition in M by N. Now we define scalar multiplication. So let us take an element R belonging to the ring R, and one element X plus N belonging to the set M by N. Here, because X belongs to M, R belongs to ring R, and M is left R module, so R into X, that will be an element of M. So by definition, the coset Rx plus N, that is the element of M by N. So we can define the scalar multiplication of element R with X plus N by Rx plus N. Now we prove that this scalar multiplication is well defined. To prove this, let us take two cossets X plus N and Y plus N such that these are equal. And because these two cossets are equal, so we can say that the difference of X and Y, that belongs to N. Now for R belonging to the ring R, because N is submodule of M, so R into X minus Y belongs to N. It means Rx minus Ry belongs to N. So we can say that the coset Rx plus N is same as the coset Ry plus N. And by definition of scalar multiplication, this element is R into X plus N. And Ry plus N, this is R into Y plus N. So we have proved if two elements are equal, then the corresponding scalar multiplications are also equal. It means scalar multiplication is well defined. Now it remains to verify the other four conditions. In the first condition, we take two elements R and S belonging to the ring R, and one element X plus N belonging to M by N. Now let us find R plus S into X plus N. By definition of scalar multiplication, which we defined already, this can be written as R plus S into X plus N. Now because M is left R module, so by properties of module, this can be written as Rx plus Sx. So this element becomes Rx plus Sx plus n. Now by definition of vectors addition, which we defined in m by n, this can be written as Rx plus n plus Sx plus n. Again, by definition of scalar multiplication, Rx plus n, that can be written as R into x plus n, and Sx plus n can be written as S into x plus n. So we have proved R plus S into x plus n is equal to R into x plus n plus S into x plus n. In the next property, we take one element R belonging to the ring R and two elements from m by n. First we have taken x plus n and second we have taken y plus n. Now we are to prove that R into x plus n plus y plus n is equal to R into x plus n plus R into y plus n. Now here let us use the definition of vectors addition. So by vectors addition's definition, this can be written as x plus y plus n. Now by definition of scalar multiplication, this can be written as R into x plus y plus n. Now because x and y are elements of m and m is left R module, so R into x plus y, that will become Rx plus Ry. So this element becomes Rx plus Ry plus n. By definition of vector addition again, this becomes Rx plus n plus Ry plus n. Now by definition of scalar multiplication, Rx plus n is R into x plus n, and Ry plus n, this is R into y plus n. So this proves this property. Now in the next property, we have R and S belonging to the ring R and x plus n belonging to m by n. We have to prove that Rs into x plus n is equal to R into S into x plus n. Here we use the definition of scalar multiplication in m by n. So this can be written as Rs into x plus n. Now because m is a left R module, so by properties Rs into x, that can be written as R into Sx. Now R into Sx plus n, that can be written as R into Sx plus n. Again here, by definition of scalar multiplication, Sx plus n can be written as S into x plus n. So we have proved this property that Rs into x plus n is equal to R into S into x plus n. In the last property, if the ring has the identity element, in that case we have identity into x plus n. Now again, by definition of scalar multiplication, R into x plus n, that becomes Rx plus n. Here in place of R we have identity element, so identity into x plus n, that will be x plus n. So we have verified all the conditions for being a module. So we can say that m by n is left R module, and this left R module m by n, that is called factor module of m by n, or it is also called quotient module of m by n. So this was how to define quotient module. In particular, if R is a field, in that case m by n, that is called quotient space of m by n.